Hello everyone, welcome to lecture 3 today. So in today's lecture and the lecture after this, which is lecture 4, in these two lectures we are going to talk about the various applications of RF technologies specific to devices. Okay, almost all of you know about the different applications of RF or radio frequency, microwave, electronics today. We cannot imagine our life without them today. But we will also talk about the devices that are used, and that will give you a glimpse of the device technologies that we are going to actually study in this course. This course is very pragmatic in a way that although we do not have a lab component, we are not going to restrict ourselves to the discussion of the physics of the device only. We are going to actually talk about in every module that we will see for a specific device technology. We are going to talk about what are the devices that are used commercially, what are the applications that are used for, what are the pragmatic or practical things that you need to keep in mind in discussing these technologies. All these things we will try as much as we can as we discuss this course here today. Okay. So today we are going to talk about the applications of RF. We will continue to the next lecture as well. So let us begin here. Okay. So to the whiteboard here, so the focus is also on devices, it is not just about the application of RF, okay, but we will build segment by segment here. So what I am going to say is that when you talk about RF waveform, this slide may look busy, but let us go one by one. When you have radio frequency waves or microwaves, what are the different things that you can think of to do with these waves? First of all, the most obvious is that we need to amplify these RF waves in many applications. You have an input wave here, you are going to amplify the signal here, and that is an amplifier. You all know amplifier. There can be linear amplifier, broadband amplifier, high power amplifier, low noise amplifier, general purpose amplifier, so many amplifiers, right? Amplifier amplifies the input signal, and amplifiers are there also in analog electronics. Analog, low frequency, kilohertz to few megahertz probably. But here we are talking about RF. RF and electromagnetic waves are inherently for wireless communication. They are, you're bringing the signal wirelessly from the nearest base station or antenna, and you're bringing it to your cell phone, for instance. So here we are talking about RF amplification. So things are a little different. But you have a power amplifier, you have a low noise amplifier, so you can amplify a signal. Then there is signal generation. You have to generate RF signals, and people use a quartz crystal to oscillate or to generate the signal, but those frequencies are not as high as gigahertz certainly. So you need to lock into that the quartz signal, and then you need to use something called VCO, a voltage control oscillator, that will basically generate the RF signal of a desired frequency, okay, a voltage control oscillator. What kind of transistors or other devices go into these amplifiers, power amplifier, low noise amplifier? What kind of devices go into these voltage control oscillators, for instance? Okay, we are talking about transistors mostly here. These are the things we need to answer in this course, in this entire course. Then there can be RF switches. If you have RF waves on your semiconductor substrate, you are going to also use or need switches. This is a switch, you see, your antenna is bringing the signal, your antenna is also sending the signal out. Okay, the signal, this is a transmission path. You are bringing the signal from your processor or baseband or whatever, and you are sending the signal out, and you need a power amplifier because your signal has to be boosted and amplified before you blast it off to the nearest base station or tower. You have to boost it up, that is why you need a power amplifier. When you receive the signal is very weak and it is accompanied by a lot of noise. You need a low noise amplifier to amplify that signal, to make meaningful sense out of that signal, and that is a part of the receiver, and that low noise amplifier needs to have a very good noise performance. Okay, so this, you can have a separate transmitter with a separate antenna, you can have a separate receiver with a separate antenna, but to save to have compactness, save space, etc., cost, integration, people have a switch. So the switch will basically switch between the transmission line and the receiving line. So that RF switch is basically between two RF signal you might need to switch. So that is one functionality. In this slide we are talking about the different functionalities, different things that you can do with RF or microwaves. Okay, one is signal amplification, one is signal generation, one is signal switch, you are switching, or signal mixing. You are mixing two signals. Okay, you have a signal of certain frequency, you are mixing with other frequency, you are generating the difference or the sum of them, and this is the basic premise of a receiver, something called a super heterodyne receiver. Okay, this was invented or conceptualized by this person Armstrong, I believe, when he was an undergrad or something, he was a grad student. Okay, super heterodyne, the concept is still same today, more than 100 years. people still use the same concept, super heterodyne receiver. What happens is that when you are actually sending a signal, your voice, you're sending your voice, it's a very low frequency signal, or your image or video, but you cannot send that signal out in space. Your antenna size will be enormously large, and also it's not practical. So you need to modulate that signal on a sine wave which is a higher frequency, an RF, a microwave, a radio frequency signal, and you modulate that RF signal. There is amplitude modulation, there is phase modulation, frequency modulation, and much more complicated digital modulation schemes where you digitally modulate that. You send it and then you receive it. You have to now do many operations on that. First of all, it's very easy or relatively much easier to process. When you have a signal processing, you have a circuit, you have a processor, it's much easier to process lower frequency signal. A higher frequency signal is very complicated to process. So you have to extract out your signal, the true signal from, the desired content of the signal from this carrier, the high frequency carrier on which it is riding. So you see what happens is that this is an example of a down conversion, and there is something called up conversion also. What is down conversion? Okay. Down conversion means your signal that you are bringing in is at a much higher frequency. You are going to convert it into a lower frequency signal so that your signal processing platform can process that signal. So you see, this is your RF signal here. This could be at, say, maybe 10 gigahertz, just giving an example. Okay, this is a 10 gigahertz signal that is coming in. This is your 10 gigahertz signal that is coming in from the space, from your antenna, from your base cell phone tower to your cell phone, your mobile phone. The 10 gigahertz signal is coming in, just an example. Okay, it's not 10 gigahertz, it's much lower, maybe 1 or 2 gigahertz. If it is 5G, it is little higher frequency. Again, 5G depends on the country. Some countries will have very high frequencies, 28 gigahertz 5G, but in India it's typically sub 6 gigahertz 5G. Okay, anyways, let's assume it is 10 gigahertz, just assume. Okay, the signal is coming into your cell phone antenna, okay, from the nearest base station, but your cell phone processor will not process the 10 gigahertz. All the signal processing, all your voice, your Instagram videos, your Facebook audios, that processing has to be done at much lower frequency on your cell phone processing chip, the GPU, CPU, etc. So what you do is that you have to down convert the 10 gigahertz to a lower frequency. So you use something called local oscillator. That could be your VCO also. The VCO is your voltage control oscillator that will generate an RF signal, okay, from a quartz crystal, whose frequency is very close to 10 gigahertz, say 10.1 gigahertz, okay, maybe 10.1 gigahertz. So when this is a mixer. Now this mixer is doing a mixing of RF waves. This mixer also has you have RF devices. What kind of devices go into mixers? That's an important question. So mixer is a RF component, you can say. It will mix the two frequencies. It will create 10 plus 10.1 gigahertz signal, which is 20.1 gigahertz signal, and it will create 10 minus 10.1 absolute value, which is 0.1 gigahertz signal or 100 megahertz signal. It's much easier to operate the signal at 100 mega, process the signal, do all kinds of signal processing on a 100 megahertz signal. So you're going to retain that 100 megahertz signal, you're going to reject that 20 gigahertz signal by using a filter. You will use a filter, it's very easy. 20 gigahertz is much higher in frequency, 100 megahertz is much lower. So you will use a low pass filter, you will filter out the frequency, and that's what is happening here. This is DC, this is a 100 megahertz. So you have down converted 10 gigahertz to 100 megahertz, and that's easy, it's called down conversion. Now when you send it out from a transmitter, you are bringing in that 100 megahertz signal and you have to send it at 10 gigahertz. So you are going to do again a mixing, it's called up conversion. You will do an up conversion to take it to 10 gigahertz or whatever, and then you will transmit to the antenna. Again you might have filters there. So this is the basic of the transmission receiving that's happening. You have so many things. You have an amplifier to amplify the signal, you have a mixer, I told you exactly, you have a voltage control oscillator, I also told you that function, you have an RF switch, I also told you that there are many others, okay, many other functionalities. For instance, you have to combine the power of RF, power combining, power splitting, you can do that on the semiconductor material, on the chip, okay, and that does not necessarily need an active device. You can use it a more passive device, you can use microstrip lines, you can use this transmission lines on the semiconductor substrate to do things like power splitting, power combining, transformers, filters, so many things are there, okay. These are passive devices, but active devices are use RF switch, RF amplifiers, RF signal generation, things like that, okay. So just please keep that in mind. Now there are this was all in the context of communication actually. If you realize, I am sending a signal, I am receiving a signal from my maybe mobile phone, maybe my radar, maybe my satellite communication, what have you. This is more like a wireless communication, which is the life, life and breath today. We cannot imagine life without this. It's so critical, right? But there are other applications. Historically going also, there are many applications. So the communication we already talked about, and you can see that there are many frequency ranges in which you are going to communicate your mobile, your Wi-Fi, your GPS, your 4G, 5G, they operate at different frequencies. Satellite communication could operate at 5G at different frequencies. Your astronomy, your radio astronomy, okay, your radar, your military communication, jamming, they could be at different application. There could be at different frequencies. Although that is not communication per se, that's electronic warfare. I'll come to that. But communication happens over a range of frequencies. Then there is something called ISM. ISM stands for industrial, scientific, medical. These are really low cost, high volume consumer application, and the frequency bands. They are exactly specified country to country, but there is a broad spectrum that is kind of allocated by the international union or agreement or whatever, and each country will have its own specific bands within that. So these are like routine use, and these are like your RFID, you open your remote control of your car, you unlock the car, you use your TV remote, for instance. Sometimes you use your electronic housing, your AC remote, heating, microwave oven, or medical technologies might also use heating, medical treatment, okay. Security, your home security, sensors, emergency calls, etc. This is from a Toshiba. I'm Toshiba, it's a company, Japanese company. Its image is from Toshiba. I'm not advertising for Toshiba. Many other companies also sell this, okay, but this image look nice, so I'm using it. So many day-to-day life activities, microwave oven, sensors, car garage opening, car remote, everything could be clubbed together under industrial, scientific, medical. Yeah, in medicine and hospitals also there's a lot of tools and equipment that will use this RF frequencies, and so this RF frequency ranges are open to all, and so you generally do not want your communication equipment or communication technologies to use those spectrum, because what will happen is that there will be a lot of interference. You can choose to, a company can choose to have its communication, your cell phone communication also at that particular frequency as one of these ISM, but then it has to be able to withstand that interference, that enormous amount of interference that will come. Imagine microwave oven, it's in every house, the microwave oven will interfere. So you have to be immune to that. So that's why people do not try to operate on this, but it's very low cost. So all the other components, accessories are very low cost available there, okay. So these are applications of RF of course. Then radar. Radar is very important. You have civilian radar like weather, meteorological radar that will predict, scan this soil, maybe for agriculture, for rain, for water, etc., etc. Then there will be military radars. Of course, this is an image from Indian DRDO website. Military radars are very important to scan the enemy skies, to look for threat like drones, maybe specifically look for missiles, aircraft, incoming threats. So radars, the more power a radar has, say. When I say power, I mean to say the output power, the more further in the sky of the enemy you can actually scan, So that's why you need a very high power radar. So it means you need a very high power transistor. What are the kind of transistors that will go into this radar? The radar also have a transmit and receive. The same communication that we talked about is also the same in the radar. Okay, in radar we call it a TR module, a transmit receive module. So it will transmit, it will receive. In communication you can call it a front end module, you can call it a transceiver, things like that. And another upcoming application, emerging application is drone. So drones use RF a lot to transmit signal, to receive signal, images, etc. And then now there is things like anti-drone, drone jammers, you jam the drone, you destroy the drone, okay. So drone detection, drone jamming, anti-drone, these are other counter drone operations that also depend heavily on RF. An anti-drone operation like drone jamming and stuff like that, you need really high power to jam the drone, okay. So RF devices with high power capabilities are also very important. So this only tells you that the space or the area of application of RF technologies is only increasing every day with newer and newer technologies, okay. So if I come to electronic warfare radar is only one aspect of it. This is anti-drone, for instance. This is an anti-drone that was inaugurated by a company in India. So there can be many electronic warfare technologies like detection, jamming, so many electronic warfare techniques and technologies depend on RF application, okay. You use the entire electromagnetic spectrum for electronic warfare, but RF and microwave is specifically very critical in that for this different jamming, detecting, missile seekers, for things like that. So RF electronics is is a very critical technology. Okay, it incorporates right from materials to device to circuit designer, RFIC designer, MMIC designer, system developers. It incorporates microwave engineering, everything. Okay, it's a very vast domain that way. Again, I am coming back to transmitter receiver because I want to talk about devices that are going to be used there. Okay, if I look at a receiver, if I have an antenna, it is an antenna by the way, it receives the signal, it has to first filter out the signal in the sense that you want to filter out the obvious unwanted frequencies. Then you have a low noise amplifier to amplify the signal with excellent noise performance, because a lot of noise is coming here also. With the signal is very weak, and there is a lot of noise. So a low noise amplifier has to have a very good noise performance, which means its noise figure should be very good. A noise figure is basically nothing but signal to noise ratio at the input divided by signal to noise ratio at the output. You want this ratio to be as low as possible, which means you want the signal to noise ratio at the output to be as close as possible to the signal to noise ratio at the input. That is all it means. It should not, the system should not degrade the signal to noise ratio at the output, that is all it means. So you need to have a very low noise figure, and then it will amplify the signal, and then I told you a local oscillator will mix the signal to create this low frequency signal. Okay, this is called intermediate frequency. The low frequency that you generate is called intermediate frequency. Then you have an intermediate frequency amplifier, you have to filter, demodulation, then all this signal, baseband signal processing will come and things like that. Okay, so all these things will come there. So this is a receiver. What kind of device is going to this low noise amplifier? Now and what kind of device is going to oscillator, what kind of device is going to mixer, etc., etc. These are the things that we need to understand. See, it depends on low noise. Let us take an example of a low noise amplifier. It actually depends on whether you are talking about this receiver inside your smartphone, are you talking about in a radar, or are you talking about in a cell phone tower or a base station where you are going to enormously send signals out. Okay, it depends on the application. This is a transmitter, the reverse of receiver. You have the signal at 400 megahertz, for instance, intermediate frequency, you are mixing it at a 500 megahertz to create almost like a 1 gigahertz or 0.9 gigahertz signal. You filter out the unwanted frequencies, you use a high power amplifier to boost the signal and then send it out. So what kind of device is using high power amplifier? We are going to talk about that in this course, by the way. Okay, again it depends on whether you are talking about a cell phone, whether you are talking about a radar, you are talking about a satellite communication, or talking about a cell phone base station. Okay. It is just an interesting statistic I thought you should know. In 2021, the total number of smartphones that were sold in the world was 1.5 billion. Can you imagine that? So imagine the market we are talking about of RF components, a low noise amplifier, a power amplifier, the RF front end module, and so on and so forth. It is enormous. This is just to bring home the point that the RF application space is growing, the market is growing, the demands are growing. Okay, things are becoming more stringent at the design front, and so it is all the more imperative for us to appreciate what devices are used, how can we improve the device, because only an improvement in the device leads to a disruptive improvement in the device technology, in the systems technology. For instance, gallium nitride was a disruptive technology that has pushed gallium arsenide more or less out from the really high power segment, at moderate frequencies. At very high frequencies still have indium phosphide, but LDMOS and gallium nitride are, for instance, the dominant competing technologies for wireless base station, okay, power amplifiers. So when you have this, this is a receiving chain, this is a transmitting chain, you have the low noise amplifier, the power amplifier, you have a switches here to switch between both of them, or this is the switch, sorry, and this is the antenna tuners. You have antenna tuners, there is also something called beam forming IC and so many, and this is the antenna, by the way. So this entire thing is the front end module, the front end module is basically the thing that sits between the antenna and the mixer stage, where you are going to mix the signal with VCO. Until that point is typically the front end, and people say the front end is typically a part of the transceiver, although the transceiver is shown here separately. Transceiver stands for transmit receiver. So the entire transceiver actually includes the front end module in general, but different vendors, different system designers, different phone companies or whatever, they might use different terminologies, slightly different. Okay, so sometimes people may say transceiver is after the front end stage. Sometimes people might say the transceiver incorporates or encompasses the front end stage. The transceiver will have many other things like spectrum sharing and all this mixing, VCO, intermediate frequency amplifier, all these things also will be in the transceiver. Okay, just to give you a feel for the because this is a very important component. Cell phone wireless communication is the most pervasive form of RF technology that is impacting our common citizens' lives every day. Everything else is also important, weather radar, military radar, industrial scientific medicine, but this is like every minute we are using the cell phone literally. Okay. In a radar, for instance, I was talking about radar. In a radar they call it a transmit receive module, and you can see there are switches to switch between the transmitting and the receiving part. Okay, that is a transmitter, you can see the transmitter, there is a receiver, you can see this is a very old one, this is from 1980s I believe. Okay, so it could be from discrete transmitters, discrete receivers that are integrated separately on a board. Okay, this is connectors, these are connectors, and these are switches. They are also phase shifters by the way, because people in radar world have been using this beam forming technology or the phased active electronically scanned arrays or phase array radars. So you need phase shifters to shift the phases, but this is a very old generation TR module, but the basic concept remains the same. What kind of transistors go into this transmitter, receiver, phase shifter, switches. Okay, and in more recent technologies people use something called MMIC. I already have used this term MMIC probably. MMIC stands for monolithic microwave integrated circuit. Microwave because it's RF signal, microwave signal. Monolithic means it's fabricated on the same die, the same semiconductor wafer. You fabricate everything, all the passives, capacitors, inductors, transmission lines, switches, active devices like amplifier, low noise amplifier, power amplifier, what have you, power splitter, power combiner, circulators, or what have you, couplers, sorry, for instance. All these things you might want to implement on the same semiconductor wafer. It's called monolithic, same piece, it means microwave integrated circuit. So now radars inherently use MMIC technologies because they make it very compact, efficient, and at very high frequencies like X band, Q band, talking about 10 gigahertz, 18 to 20, 30 gigahertz, etc., where radars might be used. MMICs are the solution. You'll see that. Okay, so this is an MMIC. This entire thing is an MMIC. You can see all these golden lines in between here, yellow light looking golden lines. They are all the transmission lines here. This is a transmission line. There could be active transistors. This could be active transistors. There could be phase shifters. There could be couplers. There could be power splitters. All these things are implemented on an exact semiconductor wafer. It could be a gallium arsenide maybe, or a gallium nitride maybe. Okay, a substrate or a semiconductor wafer technology that is there. And then this could be maybe a power amplifier. This entire thing is an MMIC, but this could be a power amplifier. This could be maybe another component, maybe a low noise amplifier. I am not saying this is a low noise amplifier. I have not read through this paper, but just to give an example that MMICs are used extensively in radar. This is another MMIC. One of them could be power amplifier, one of them could be low noise amplifier, one of them could be the switch, right? They are MMIC, each of them is an MMIC, and then they are integrated on this entire board. And this makes you the TR module, at X band. X band is 8 to 12 gigahertz. So it's going to operate in that. There could be a spot frequency, maybe 9.6 gigahertz. It's X band. So at 9.6 gigahertz, I'm going to operate this particular. I'm just giving an example. Okay, these are also transmission lines. It's a power splitter, power combiner. Okay, you're going to split the power, you're going to combine the power. There could be driver stages, pre-driver stages to boost the power level so that you can feed into the power amplifier. Okay. The power amplifier will be on the transmitting side, the low noise amplifier will be on the receiving side. So these MMICs, it's very complicated to design by the way, and then you need to work with a foundry which will have this PDK, the process design kit, using which you design this MMIC and then you get it fabricated, tested, etc., and then you build this TR module. Nowadays, this is from 2008, nowadays in 2023, 2024, people are even releasing entire TR module as an MMIC on a single MMIC die, say gallium nitride. In gallium nitride there are companies like Fujitsu, like Qorvo. These companies are releasing this entire TR module on a single gallium nitride wafer. It's a TR module MMIC. It's an MMIC TR module where the low noise amplifier, the power amplifier, the switch are basically integrated together. I am not sure about the phase shifter, but they are all integrated together on a single die in 2023 as we talk today. Okay, these are for military radar specifically, and in military radars you cannot go to a radar website and see in military radars what are the components that they have. It's very strategic, very confidential of course, but from the literature and from the companies that sell these different modules, etc., that these are for strategic applications, for instance. Okay, so this is a schematic of an MMIC. As I told MMIC, I wanted to just tell you MMIC. This is a transistor, field effect transistor. This could be an inductor, a spiral inductor that will have some inductance value L. This could be a capacitor, maybe a parallel plate capacitor. There's a metal below, there's a metal above, and in between there could be a dielectric that gives you certain capacitances in maybe picofarads. This could be inductor in some nanohenry. There's a resistor. Okay, this is a via hole. What is a via hole? Via hole is like you etch through the substrate to create a hole to the back side, so that in the back side you can have a metallic plane, that is a ground plane. You short that top ground with a bottom ground, so you have a global ground plane, you take the heat away better and you reduce the inductances. You don't have to wire bond out, it's a back common global ground plane. So you reduce, and you see all these serpentine lines, all these radial stubs and things like that. These are all different components of microwave engineering. You might have power splitter, power combiner, a stub, a impedance matching network. What is impedance matching? Your everything should be all matched to 50 ohm. That's like a holy standard. So the impedance of the transistor on the input side, on the output side, they could have different impedances. They could have say 25 minus 45 J ohm complex, right, or maybe 21 plus 46 J ohm. That's a complex impedance. Okay, you want to match it to 50 ohm, so that's called impedance matching. Then it's basically matched. So that matching has to be done through impedance matching networks, and radial stubs, these are called radial stubs for instance, or maybe these are something else. They have different kinds of, there could be filters also by the way. Okay, they have different kinds of components on an MMIC, so that the entire is an independent circuit on its own. Okay, entire could be an independent circuit on its own. Okay, this is just a schematic to show that this is how an MMIC looks like. Maybe I can remove the annotation. So this is the side view of an MMIC. You see, not MMIC only, MMIC chip. You can see this is an MMIC. This is on a package. QFN stands for quad no lead package essentially. Okay, quad flat no lead package. It's a simple package. It's a MMIC is on this top of this. This is another low noise amplifier MMIC. This is maybe a power amplifier MMIC. This is also a package. This is the platform on which you have. This is the power amplifier. You see. Okay, this is the connector that will take you outside to the external world to connect to the instrument or maybe the system, and there could be via holes. These are via holes can come top ground and the bottom ground are all shorted, so that there is a ground plane and there is a via hole. Okay, so this is how the side view looks like. Now this is, for example, I want to come to a device that is used in an active military radar. So in a military radar, what kind of LNA, low noise amplifier, could be used? I told you a radar should have a low noise amplifier, power amplifier and a switch and a phase shifter in the TR module, the transmit receive module. So what is the device that is used to make a low noise amplifier in a military radar? So this is a company called Analog Device. Again, I am not advertising for this company, I am just picking out from the internet. There are other companies also that sell. You see, this is an image of the block diagram of the low noise amplifier that they have, and what is the device that they are using? They are using a gallium arsenide HEMT. P stands for pseudomorphic. This is precisely one of the devices that we are going to talk about in this course later on. Pseudomorphic HEMT. HEMT stands for high electron mobility transistor, and this is an MMIC. I told about MMIC, and this is a low noise amplifier. It will operate from 0.3 gigahertz to 20 gigahertz. Can you see that? Pseudomorphic HEMT is, in this course we will talk about gallium arsenide pseudomorphic HEMT among other devices. So you can see that what is HEMT? A HEMT is a device where you have a barrier layer and then you have a channel. There is something called a two-dimensional electron gas. What did I draw? I am drawing the conduction band profile, and this is the valence band profile. So this is gallium arsenide, this is say aluminum gallium arsenide, this is an alloy, a larger band gap alloy, and this is the Fermi level, this is the conduction band, this is the valence band. Okay, and there is a high density 2D electron gas that is kind of confined with the interface of these two layers of material. It gives very high mobility, many thousands of value of mobility. It is called high electron mobility, and this layer is strained to the layer below. There is a lattice constant difference, it is strained below, and that is why it is called pseudomorphic. We will come to that by the way. Okay, in a much later part of this course we will talk in details about pseudomorphic HEMT and their status. So you can see in a military radar people use a gallium arsenide pseudomorphic HEMT to make the low noise amplifier. You see its low noise figure is 2 dB, that is very low noise figure. It is a good low noise figure, but not a record low noise figure. People go even less than 1 dB, but maybe for this particular application it does not have to be below 2 dB. So 2 dB is the signal to noise ratio at the input divided by signal to noise ratio at the output. Take log of that. Okay, it is a 10 log of that, it is your signal to noise ratio, it is your dB, 2 dB, that is what it is called. P1 dB output power, what does it mean? It means at 1 dB compression, you will see what is 1 dB compression, we will talk about that in subsequent lectures by the way. At 1 dB compression point, okay, essentially if you have an output power and if you are plotting with respect to input power, then the power increases linearly I mean the input power, then it saturates, okay, which means the gain stays constant, then the gain comes down. So if this gain is, this constant gain is say 20 dB, then the point where the gain comes by 1 dB down, which is 19 dB no total, that point is your 1 dB compression point. So at that 1 dB compression point, the output power is 15 dBm. That means this 1 dB compression point, you have 15 dBm output power, 10 dBm is 10 milliwatt and 20 dBm is 100 milliwatt. So this device is somewhere between 10 to 100 milliwatt, maybe 20 or maybe 30 milliwatt, you can calculate exactly. So that's it here, okay. So these are other parameters that are there, I am not going to talk about that, but this is just to show you that gallium arsenide pseudomorphic HEMT technology is used in a military radar LNA, okay. It's satellite communication. Satellite communication needs very high power, several hundreds of watts of power, and it's very power demanding, you know, you need very high power amplifier to transmit signal. I am talking about a transmitter by the way, okay. So you see there are many techniques to kind of have this worked out, because historically and even today such high powers of few hundred watts or few tens of watts at very high frequency, when I say very high frequency, maybe Ka band is say 28 to 40 gigahertz, that is a really high frequency. At that frequency if you need hundreds of watts or maybe say 50 watt or 100 watt, it is almost improbable that a semiconductor technology will give you that, really. MMIC is, I told you, at that high frequencies you have to use MMIC, okay, for various reasons, and single MMIC giving that kind of power, a 100 watt power at say 40 gigahertz does not exist today. It's too difficult, too challenging. So historically and even today the dominant technology that is used is actually vacuum tube. Although we think vacuum tubes are gone, they are not actually gone. Satellites they use vacuum tubes a lot for transmitting power, because to transmit power like 100 watt at 40 gigahertz you need a vacuum tube, maybe hundreds of watts, maybe kilowatt. These vacuum tubes can go up to tens of kilowatt at higher frequencies like that. It's insane, it's crazy high. You cannot have semiconductor device technology at that level. What is this vacuum tube? Typically this vacuum tube is a travelling wave tube amplifier. We will not talk about that, but it's like you have a tube, you have a cathode that injects electron beam, and then you have an input signal on the RF that will interact with this beam, and it will basically amplify with some mechanism, etc. Okay, so it's a travelling tube amplifier. It's very high power, it can give you high power, but it also needs very high voltages, it also needs very large space, efficiency is an issue, it is very bulky, maintenance is expensive, it is also very costly by the way. So people are increasingly trying to get to semiconductor technology for satellite communication. So MMICs are used and people are trying to push how much you can go with MMICs, semiconductor device technologies. Again, what is the question is what kind of device, I mean this is very high power, so it has to be mostly gallium nitride, okay, it is very high power. People use different techniques. For instance, I can use different MMIC with different MMIC. See, MMIC can be used for LNA, low noise amplifier, it can be used for mixer, it can be used for anything, but here I am talking about MMIC PA, power amplifier. MMIC can be used for anything, okay, mixer, low noise amplifier, etc., but I am using it for PA, power amplifier. So I can combine the power of many power amplifiers, MMICs, and combine them and send it to the antenna. This is one technique. Another technique is that these are antenna elements. I have different discrete antenna elements, and one MMIC element is feeding one antenna element in a beam forming kind of a configuration. But please remember that still semiconductor technologies such as gallium nitride are still far away from achieving the power levels of travelling wave amplifiers, okay. I will come to this image, this is what it means. You see this is the power level and this is a frequency, this is your semiconductor device technology, okay, and this upper is your vacuum tube. You see the kind of power you get, even at 100 gigahertz you can get hundreds of watts of power, absolute power, it is crazy high. Semiconductor technology is trying, SSPS stands for solid state power amplifier, where you basically combine like this lot of these power amplifiers you combine, okay. So semiconductor technology is advancing, trying to reach the vacuum tube threshold, and vacuum tube technology also advancing by the way, okay, just to give you a feel. This is very critical for satellite communication. This is the image of one power amplifier MMIC. Can you see that? There is all this transmission line in yellow, all these power splitters, power combiners, balloons, transformers, impedance matching networks, all have to be very accurately designed by the way, based on a design kit that is provided to you by the foundry, and this is a power amplifier MMIC, and many of these MMICs are combined. Here it is combined to get a large output power. Okay. So just keep that in mind, please. Now this is all about very high power amplifiers. These are used for satellites, military radars. I also talked about low noise amplifier, by the way. Let's come to smartphone, let's come to cellular base station, and let's see what kind of devices go into those components in those. Okay. So maybe that we will take in lecture 4 next class. So what I will go is that I will end today's lecture 3 here. I believe we have had sufficient introduction to application of RF technologies and also the flavor of the device, things like MMICs and things like that. So thank you for your time for today's lecture. We are going to switch to lecture 4 next, okay, and I will see you there. Thank you.